Hi, this is Mr. Rikes, and I'm going to take you through a couple of quick thermochemistry problems that you may see on the test. First one talks about a sample that's going to be placed in water, and basically the water temperature changes or rises from 25 degrees Celsius to 32 degrees Celsius. So one of the things that we can say about this is that the energy that the water gained is the same energy that was lost by the object. So if we can determine the amount of energy that the water gained in joules, we can say that the object lost that same amount of energy. And then we can solve for what we're looking for in this particular problem, which is the specific heat of the substance, knowing that value. So you can set this up one of two ways. The first way we can do this is we can take our Q value, Q is equal to MC delta T, and we can refer to the water. And we can solve for the joules that the Q value for the water, which is the joules that the water gains in energy. So we take the mass of the water, 150 grams. We multiply that by the specific heat of water, which is 4.184 joules per gram degree Celsius. And then lastly, we can multiply that by delta T. And delta T can be solved by taking the final temperature and subtracting from it the initial temperature. So 32 minus 25, which gives us a delta T of 7 degrees Celsius. And what we get for Q value is Q is equal to 4,393.2 joules. That's the amount of energy that the water gained, which means that's the amount of energy that the substance lost. So then what we can do is we can take that value and say, well, the substance lost that energy, so it's remaining at a negative 4,393.2 joules, and then put it into the expression where the mass of the substance, 60.0 grams, that's a 0 there, times the specific heat, which we don't know, the C, times the delta T for this substance. And we know the substance started at 70 degrees Celsius, and anytime we put two substances together, they are eventually going to reach equilibrium. So that's where we get the 32 degrees Celsius. So the substance final temperature is 32, initial temperature is 70, so we end up with a delta T value of negative 38. Now, because we made the joules value negative here, and we made the delta T value negative there, the negatives are eventually going to cancel each other out. And so now we can rewrite this expression and solve for C. And if we solve for C, we are going to get a value of 1.92 joules per gram degree Celsius. And that's our specific heat for this substance. Now again, as I said earlier, we could redo this expression. We could do it a little bit differently. We'd still get the same answer. And so I'll just very quickly, if you understand this, you can skip ahead to the next problem, but you may have set it up like this. Q is equal to negative Q. So we can replace Q with MC delta T. This would be for the water on this side. It's gaining energy, and then the substance, whatever the substance is, on the other side, which is negative, so negative MC delta T. Then we do the same thing we did before. We plug all the values in, so we have for the water 150 grams, specific heat of water is a 4.184 joules per gram degree Celsius, delta T for the water was 7 degrees Celsius, and that's going to be equal to the negative 60 grams. Again, our unknown value is C, times delta T for the substance again, which is a negative 38. So again, we on this side, degrees Celsius. So on this side we have the negative value here and a negative value here, which will eventually cancel each other out. And if we do this entire problem and we solve for C, we will get, again, C is 1.92 joules per gram degree Celsius. So that's how we solve that particular problem. All right, let's look at the next problem. What amount of joules is necessary to heat 42 grams of water from 30 degrees Celsius and boiling it all the way? So, again, what we need to know is we need to know that there is a temperature change, right? In order to boil water, we know that it has to reach 100 degrees Celsius. So our final temperature of the water is going to be 100 degrees Celsius. So we can do our Q is equal to mc delta T. And we'll start with that. And the first Q value we get is the mass of the water, 42 grams, times the specific heat of water, which is 4.184 joules per gram degree Celsius. Now times the delta T for water, and the delta T is a final temperature we said was 100 minus the initial temperature, which is 30. So the water has gained 70 degrees Celsius. And we're going to solve for that, and we're going to get a Q value of 12,301 joules. Okay, now the other thing is if we read through the problem, not only did we bring the water to its boiling point, but it says we boiled it all away, which means now we have to deal with the phase change. We've now taken all of that liquid water and we've added so much energy that it's created now water vapor. So you'll notice that I gave two different values there. I didn't mean to cross that out, but the heat of fusion and the heat of vaporization. Well, guess what? I crossed it out because we're not going to use the heat of fusion. Just like on the test, you need to know which one to use. Well, in this case, because we're boiling water, we're using the heat of vaporization, 2260 joules per gram. So we want a second Q, and the second Q is going to be the mass times the heat of vaporization. The mass, we said, is 42 grams, and the heat of vaporization is 2260. And we're going to multiply those values together, and we're going to get a Q value of 94,920. So to finish this problem, what we want to do is we just want to add the two values together for the total Q. And if we add those two values together, we're going to get a total Q value of 107,221 joules. And that is the correct answer for that problem. All right, let's move on to the last problem. The last problem talks about what would be the final temperature of ice if 1800 joules were removed from 25 grams of water at 15 degrees Celsius. So the first thing is, what's going to happen to get 25 grams of water to ice at a temperature starting at 15 degrees Celsius. So we're going to do Q is equal to mc delta T. And we're going to see how much energy has to be removed to change that temperature. So we're going to have the mass is 25 grams. We're going to have the C value of 4.184 joules per gram degree Celsius. And we're going to have a delta T value of negative 15 because we were going from zero, final temperature of 0, from a temperature of 15. So 0 minus 15 is negative 15. And we're going to get a Q value there. And Q comes out to be negative 1569. All right, so that's the first step. Second step is phase change. How much energy is it going to take to change this 25 grams of water to ice? So we're going to do Q, and we're going to say we have 25 grams, and we're going to multiply it by the heat of fusion, which is 333 joules per gram. And when we multiply that together, we get a value of 8,325 joules. Okay. Now, we said that we are freezing the water, so we know that the energy is leaving the water, so we're going to make that a negative. So, now we started off removing 18,000 joules. We have now dealt with the decreasing the temperature of the water to freezing, and then freezing that water. And so if we add those two values together, we'll be able to see how much energy we have left to decrease the temperature of the ice. So when we look at the difference between those values and this value, we still have an extra 8,106 joules of energy that we're now going to use to remove from the ice. So now what we're going to do is we're going to solve for delta T. And we're going to say the joules of energy removing is the 8,106. And we're going to say that that is equal to the mass of the ice, 25 grams of ice, times the specific heat of ice, which is 2.06, I believe. I hope that's the right answer. Joules per gram, degrees Celsius. And then, obviously, we're solving for delta T. So now we just solve for delta T. And what we end up with for delta T is a negative 157.4 degrees Celsius. So, the final temperature of the ice, negative 157.4 degrees Celsius. So that's how you solve that type of problem. All right, we'll see you in class. Good luck on the test.